lunch is at 12.
Yes, so I'll give you a 5-minute warning.
Yeah. I cut into lunch.
Sure. Okay, guess we'll get started. Yes. Good morning, everyone. So I know this is the last session before lunch, so please bear with us. We have here Dr. Brian Mesmer from the University of Alabama in Huntsville. He'll be presenting on his research on ART-016, Integrated Mission Equipment Architecture Process for Vertical Lift Systems. So Dr. Mesmer is an associate professor in the Industrial and Systems Engineering and Engineering Management Department at the University of Alabama in Huntsville. He's established the Imagining Engineering Systems lab at UH in 2016 to examine preferences in systems engineering. His research team includes graduate and undergraduate researchers who explore non-traditional disciplines, including the use of gamification in training, the communication of preferences through storytelling, and the study of performance metrics of large-scale engineered systems. With that, over to you, Brian. Thanks.
Hi, everyone. So today I'm going to be talking about insights on making decisions concerning architectures. So a lot of this is going to be application of methodology and techniques that we've already seen in other engineering fields and applying it to architectures and seeing how we have to modify it when we're making these architectural decisions. So the motivation for this project was to enable a rigorous, repeatable, systematic approach to architecting. And the real issue here was the need for a justification of our decision making. So we know not only in architecting have to justify our decisions to the current stakeholders, but also the stakeholders 40, 50, 60 years down the road, asking why did we make that decision? And right now there's not a good way that we document it, and there's not a good way in which we rigorously make those decisions in order to provide that justification. And then of course a general desire to improve architectures along the way. The research goal of the project was to develop a decision-making process for architecture decisions, and we do that by looking at 5 different steps. So the first step is figure out what the decision framework is going to be. The next 3 steps actually come from the decision-making framework that we choose, which are going to be inputs of preferences, beliefs, and alternatives. And then step 5, which has been a recurring question over the last 2 years working with the Army, has been on the separation between designing and architecting. And so I'll let that sit for a little bit. And there's lots of opinions on the differences or non-differences there. So the first step, what is, and I wish I could move that guy a little bit, but I don't think I'll be able to, but that's okay. So the first is to establish a decision framework. So the question that we asked is, what is the current decision-making approach in architecting? And the vast majority of it is heuristics based. Any architecting handbook that you see, any textbook or article is typically focused on what are the heuristics to good decision making in architecting. That's fine if there's good evidence to support those heuristics. And what we did was a study of 4 of the main sources, 3 textbooks and 1 main paper in the architecting community, examined the heuristics that they're proposing and looked at their citations that they have for those heuristics. And we see that 156 out of roughly 240 or 50 or so have no evidence whatsoever. And 64 have case studies, but those case studies are vastly different from architecting. And a lot of them are actually sports. So they're baseball and football case studies. So that's a little bit of a worrisome foundation for decision-making. Heuristics are fine as long as there's clear supportive evidence. And we did not see that in the sources that we examined. So the next research question would be, well, what decision-making approach should architects be using? And there's some unique challenges in architecting that approach should be addressing. So there's uncertain outcomes, there's extended and uncertain timing of the outcomes, there's uncertain future stakeholders, and those stakeholders aren't just people above you that you're answering to, but they're also future implementers, end users, decision makers, designers, the whole gamut. And there's going to be multiple stakeholders. These things we see in traditional design engineering and systems engineering, right? None of this is unfamiliar, except for it's much more greater. So the uncertainty is much more greater. The number of stakeholders is much more greater. And so these are going to be interesting challenges as we go forward. There's many different options to choose from. Here's just a typical list: QFD, Pew method, AHP. All these are decision-making approaches. All of them have common issues, some more than others. The common issues are inaccuracies in preference measures. They're generally non-repeatable. at least by different decision makers, and there's they're incapable or non-rigorous incorporation of uncertainty. So some to varying degrees, more than others. Two words that I'm highlighting here, preference and uncertainty, because that directly relates to the challenges that we saw, where there's high uncertainty and multiple stakeholders which have multiple preferences. So then a proposed decision-making architecture or decision-making framework that we could use for architecting decisions is a technique that is normative. So normative here means how should people make decisions, and mathematically rigorous, so that we can have justifiable and repeatable decisions. We can leverage information that we currently have in the engineering community, and a lot of the techniques that we would use to meet those criteria would be normative decision theory. And so normative decision theory is a mathematical way of how people should make decisions. And there's three main inputs to that theory, which is understanding the alternatives, understanding the beliefs on the outcomes of the alternatives, and understanding the preferences on the outcomes of the alternatives. So those three pieces are going to be the things that we need to be able to use normative decision theory. Within normative decision theory, there's many different theories to use. Here, what we're proposing is expected utility theory for single decision maker and Bayesian game theory for interacting decision makers. Again, none of this is new for any design engineers in the room, but as we move into the architecting, there's going to be some more challenges. The figure that we see down here at the bottom is pulled from Dr. George Hazelrig's textbook, and it's basically this framework for normative decision making, where we have preferences, beliefs, and alternatives feeding in to the process. And along the way, we have outcomes that are formed. We have a decision criteria, which he pitches as expected utility that's used. We optimize that and we get a preferred alternative. So high level overview of normative decision theory. So if we're going to go through that process, then we have to look at those three inputs of normative decision theory: preferences, alternatives, and beliefs. So if we look at preferences first, the question would be, well, how are architectures currently assessed? Since that's what we need for preferences. And ideally, what we would be looking for are architecture metrics and architecture preferences. So here we have three architectures, and we measure them in some way with three A, B, and C metrics. And using those metrics, we're able to say, hey, architecture 2 is better than architecture 1, which is better than architecture 3, right? We are able to show our preferences. So we have a preferred ranking on the right, and we have the metrics in the middle. Either of those would be great if we had, because then we could use that in order to feed our decision-making process. We did a literature review, pretty deep dive. We could not find anything to really assess architectures that's currently used today. That's an issue for decision-making, huge issue. All of the ways that people talked about assessing architectures always looked at the system at the end. There is no way in the process to say, is this architecture good or not? And that was a challenge, right? If we're designing an architecture, we should be able to assess the architecture. There's a note here. If you're aware of any ways to assess architectures that are currently being used, please let me know, because we are fresh out of ideas on what search topics to be looking for, and maybe we're just missing some keywords. But overall, the system, the stakeholders and the implementers are really used to talking about the systems, but not really used to talking about architectures and how to assess them and how to measure them. Okay, so that's what's currently being done to assess what could be done to assess. And we would look towards value modeling as a way to assess architectures. Here's some definitions pulled mostly from the work of Paul Colopy, who's kind of the leader in the field. And the key one here is the second one. It takes in all relevant attributes of a system. Here, system is architecture, and delivers a measure of preference for the architecture. So if that's the definition that we roll with, and all these definitions will work with each other. But the second one is what we focus on, then the word attributes here stands out. And the question would be, what are the possible attributes for an architecture? Which takes us to our next question. What are the possible attributes, specifically looking at the Army stakeholders, since this was an Army funded project? So findings from the Army that we didn't, our team didn't look at, but that was provided to us, have stakeholders from workshops discussing business drivers. So they care about things like cost and schedule, and life cycle quality attributes, things like maintainability, robustness, your illities. Work done by SEI is taking the quality attributes. So the illities more or less here in this example, maintainability, robustness, and so on, and breaking those down into something that's measurable, right? You talk about ilities, and if you question 20 people on an ility, you'll get 30 different definitions, right? A study that we did with NASA looked at affordability, and we surveyed 40 different people and we got 50 different answers. So they're impossible to get a group to get individuals to agree upon, but it is possible to get a group to agree upon those quality attributes, which is work that's also being done related to the Army. But they're getting measurable pieces of those quality attributes that we're calling quality characteristics. So then if we have all these pieces, if we have quality characteristics, which are the measurables for the architecture, which is work being done currently by SEI, and if we have these quality attributes that have been identified by the Army in different work, and we have business drivers, which are things like cost and schedule, then we might be able to get that into a value model to then say this architecture is worth this and this architecture is worth that, and be able to rank them. Worth here not being money, but worth being value. That's ideal. That'd be awesome. However, there's lots of different issues that we are running into with the Army's work on this. So between all these categories of things, quality characteristics and attributes and business drivers, things that build up to up further and further up to the value model, we have a lot of unknown relationships and a lot of non-quantified relationships. Work that's currently being done by the Army is catching the trends in these relationships. So this quality attribute positively affects cost and negatively affects schedule and those kind of relationships. That's great. It gives us a direction to point to, but it doesn't give us the meat that we need for a value model to really make decisions. It just kind of points us in a direction. So we see here a lot of relationships unknown or not quantified. There's work being done in the Army about the quality attributes of whether they're functions or whether they're sets of characteristics. And there's a lot of assumed relationships that are supposed to be developed through analyses or discovered through analyses that have not been attainable yet. But in order to move forward, instead of using this scenario, which has lots of different questions on each of these couplings, we're going to, which is what that captures, we're going to collapse it down and just say, okay, let's worry about quality characteristics, the things that SEI is being able to measure about the architecture, and let's form a value model around those. We still have issues. There's still a lot of assumptions on taking an architecture and being able to determine its quality characteristics, its measurements, attainable through analyses, hopefully. And similarly for the quality characteristics to forming a value model, we have a lot of assumptions that there's analyses that exist and a lot of assumptions that we can elicit these preferences from the stakeholders. So lots of open questions concerning that bit. But in order to proceed, we're going to assume that we can get that value model for now, understanding there's a lot of open questions. So when we talk about that value model, what do we mean? What are the stakeholder preferences that may exist? Well, through work with the Army, we've seen that there's some business driver focuses. So some people really care about the cost and the schedule and the capability and different combinations of those. There's people who focus highly on quality attributes. So all those ilities, the buzzwords, maintainability, robustness, interoperability, they care about those things. Some people care about the flexibility of the architecture. So an ease of adopting to new stakeholder preferences that requires little work. So as the architecture flows through, all the stakeholders are happy with it, with little changes. The effort of implementation. So when you get further down the line, the architecture is easy to use and easy to adopt and be used by the designers and the end users. And then, of course, there's lots of many other potential preferences, but these were the ones that were seen most frequently with work by the Army through workshops with the stakeholders. In general, we're just going to say the preference, a measure of preference is value, just to be able to move forward. Okay, so if we have this value, then how do we incorporate preferences over time? So ideally, we have everything at time 0, everything's great. We have these value measures for architecture 1 and architecture 2, and you either pick the highest or the lowest, whatever you care about, right? So if you're minimizing cost, you pick the lowest. If you're maximizing value, then you pick the highest. So that's easy. However, architectures span a great time period, and we're going to have different value that's generated by the architecture over different time periods, and it's likely not to be constant. So we can imagine that the perceived value generated by the architecture is something like this. Very changing over time. To kind of solidify this a little bit more, you can think about this as the amount of effort needed to develop or use the architecture at that time period. And so that effort might change over time if that's what they care about in terms of their preference value. This is pretty straightforward in terms of the traditional methods that we use in engineering. So this is engineering economics right here, where we can take this future value of the thing and collapse it down to the present time to make a decision. Right. So that's pretty straightforward. And mathematically, the trick here, that's still an open question, of course, is what is our discount rates to take these future amounts and bring them to the present? And that's a big challenge. Pretty straightforward in terms of money. The government actually can define what that percentage is going to be. 8 to 10% is typical, but here we don't even know what value is yet to be able to collapse it down to the present value. But mathematically, that's how we would go about doing it. So again, open research question. All right, so we can do it over time, theoretically. Now, what about multiple stakeholders and incorporating changing stakeholders? So over the time period, we're going to have different stakeholders that are going to be represented over time. So here we have 4 different stakeholders, A, B, C, and D. And you can think of them as generals and project managers and system designers and all these different people who are going to be caring about the architecture, and that we as the architect care about as well in order to make it relevant to the problem. And all these different stakeholders may have different preferences, in fact, are likely to have different preferences. And so how do we deal with those? So this is something, again, that we deal with regularly in other fields of engineering. So we can think of demand models. So in demand models, we have lots of different customers that are going to be using a product, and we have to be able to capture the different demands of those customers in order to determine how in what demand our product is going to be at different time periods. You can think if we're developing a new car that's going to be the same style for 5 years, and we know that the competitor is going to come in 3 years later, there's going to be a decrease in demand likely in our car for years 4 and 5. And we do this typically in industry all the time, especially in commercial products, not so much in the military. But we have the tools. So it's typical to then look at the demand of the customers over these time periods. And each of these demands over each time period is really a similar graph where we have that customer, that person caring about the thing for its project horizon. So here at time period, let's say 10 without counting, we have a person, a stakeholder who cares about the architecture, and they care about it looking into the future, right? It's not just at this moment, this is how much I care about it. This is how much I care about it in the future, and I can collapse that down to a net present for that person value. And that's what we would do here for these demand issues, but now we're changing into value issues. So we have these perceived value generated at each time period. We have different stakeholders with different preferences. There's a lot of tricks that we have to do here in order to get the math to work right. The first trick is that all of these values from the stakeholders need to be in the same units. Otherwise, when we go to collapse it down to the net present value, it won't work. It doesn't make sense. So trick number 1, we have to get all of these into the same units. Open research question. And then the meaning of the value at the time period is dependent on the decision maker's preferences. So it's the architect looking at these and saying, this is how much I care about this person's demand or this person's value. Again, significant research challenge. So an example here, so the preference of the architecture is to assume, let's assume that the preference of the architect is to assume that the stakeholders want to the preference of the architect is to ensure stakeholder approval of the architecture over its lifespan. So they want the approval of all these stakeholders as we go off in time. And for each of these spots, each of these time periods, we would look at that and say, okay, that value is the net present value of the architecture for stakeholder B for time periods, whatever their project horizon is, and we would collapse it down. So just like the demand model, we would do it similarly here for the architecture. Again, with the concerns of keeping the units consistent so that we can do the mathematics behind it all. Working with the Army, we asked the question, well, what are some likely preferences that change over time for the different stakeholders? And the expression is that the early time period would have project progression, quality attributes as the things that people care about. And as we go through time, we get to more system completion, system functionality preferences. So not only is it mathematically, we believe that there's going to be different preferences. In fact, there must be different preferences if we have multiple stakeholders, but through the Army's workshops, we see that there's going to be different preferences as well. So this is a legitimate concern. To throw even more issues on top of this decision-making process, we not only have changing stakeholders, but we have stakeholders that may overlap. So before we had 4 nice stakeholders, each with their own little time block. But in reality, we have stakeholders such as stakeholder B, who might impact from time period 2 all the way to time period 14 and overlap with 3 other stakeholders. Well, that's a challenge. So now that block there of red not only is the preferences of one individual, but it might be the preferences of 4 or 5 or 6 individuals, right? So right here, we have 3 individuals that are going to contribute to what's the worth of the product. And so group decision-making techniques have to be used to aggregate those preferences. Lots are out there, lots have assumptions, and all have assumptions and limitations. The proposal would be to use a game theory-based methodology in order to aggregate those preferences, but that is at the fringe of our work right now. So those are all the issues that we have to deal with for preferences. The next input to the decision-making process, remember there's 3 preferences, beliefs, and alternatives, would be beliefs. So how are we going to deal with that? And so the first question that we asked was how to incorporate uncertainty of a value at a specific time period. So risk neutral, easy peasy. We have potential values at a time period. We have probabilities associated with those values, and we calculate the expected value. So mathematics, pretty simple there. What happens though if we have non-neutral risk preferences? Well, we can use expected utility. So we have the same probabilistic value representation down at the bottom. We would transform that through a utility function, and then we would find the expected utility there and use that for our comparisons of different architectures. The trick here, of course, is getting those risk preferences. Again, the math is there. The math has been used in all sorts of different engineering fields in the past, but we're now talking about a risk preference that's not on money, but that's on a value. And so that's going to be a challenge. Okay, what about the stakeholders? So we talked earlier about uncertainty on the outcomes and uncertainty about the stakeholders. Well, we might not know who stakeholder A really is. And when I say really is, I'm talking about their preferences. We might not really know their preferences. Do they care about which business driver? Do they care about flexibility? Do they care about effort? We don't know, but we might have some probabilities about that person. And so here we could do the same kind of math, right? So we have probabilities related to a version of stakeholder A and a version of stakeholder A in another universe and a version of stakeholder A in another universe, right? And we can collapse those with an expected utility now and use that for our mathematics, right? And this keeps going, right? So now then we have different combinations of stakeholders and the probabilities related to each of those combinations. And then we have the lengths over the time periods for the stakeholders and different combinations of that. So it gets very unwieldy, right? But the mathematics is at least solid. So if we're able to capture those uncertainties, which is a huge open research question, I know, but if we're able to capture those uncertainties, the mathematics is there to provide us a path forward to, again, justify the decision instead of just using heuristics. All right, so then looking at the alternatives. So this says determine architecture's alternatives at the top. So what decisions define an architecture? So the Army has ongoing research that we're associated with, and they've identified different mechanisms for architectures. So mechanisms here would be if you're designing a piece of lumber, it would be the length and the width and the height and the material, right? It's the things that you have control over, right? As an engineer, a design engineer, I could control those things. Same thing for an architecture. There's decisions that we can make that we can control. Right, we can talk about a network within an architecture and how that's going to be passed along. There's a little bit of challenges here that we're going to talk about in the architecting versus design slides about not just controlling the architecture's design, but also controlling the architecture's design process. The Army is creating a list of alternatives, which we're calling mechanisms here, concerning an architecture. However, it's very improbable that we can create an exhaustive list. So what we have to do is train architects to be able to generate potential decision categories and decision alternatives. So what are the, you got to be able to say this thing has a length and then figure out, well, this thing has a length of 2 feet and 3 feet and 4 feet and whatever it might be. All right, so kind of the overriding question that's been popping up in this 2-year-long research project, and especially for the last year, has been looking at designing and architecting and differentiating between the two. Since a lot of what I'm proposing here is really design engineering stuff, right? Nothing's really unique here. It's just a different application, right? And I fully express that. So things that might be different here. So in architecting, things are not very easily measured, right? In design engineering, we can measure things, right? Here, we don't have thrust, we don't have speed, we don't have weight for an architecture, right? What is an architecture? So we need to be able to come up with those ways to assess those things that we can actually look at. And one of the reasons why we can't do that right now is that we don't have the tools to analyze the architecture during the decision-making process. We don't have CFD, we don't have FEA. What are the tools that are out there that really assess an architecture, right? And if you just say they're heuristics, I have issues with that, right? Because we don't have heuristics in CFD. We don't have heuristics in FEA. The architecture decisions not only impact the decision space, so restrict the design decisions, but they also restrict the way that we go about those decision-making processes. There might be standards and policies that we push through the architecture that changes how we make the decisions. That's different from design engineering. Typically, we have just restrictions on design space. So we have constraints and requirements that collapse down. But here, it's also collapsing the design process, the decision process. The obvious ones are the time horizon is significantly long with extremely high uncertainties, right? I think that we all recognize that. And there are many stakeholders along the time horizon. Not only that are using and implementing the architecture, but that could kill the architecture. They could say, we're done with this one, let's restart, let's do something new. And while we can see that in design engineering, because the time frame's a lot tighter, it's not as often as we would see it in architecting. So if we take a step back then, the normative decision approach that we're proposing to use in architecting is really unchanged from design engineering. Again, there's nothing new in the actual process or the actual framework. The challenge is solely in forming and representing the 3 inputs of alternatives, preferences, and beliefs. And that's where the focus of architecting, I believe, really needs to be if we want to be able to justify our decision-making to future stakeholders and to current stakeholders. All that's changed here from the previous George Hazelrig figure is that I got rid of expected utility and I just have decision criteria. You're asking why I talk about expected utility throughout this whole thing. There's a lot of questions about expected utility because the assumptions and the theory that really form it and give it some meat assume that you're having repeated decisions. And we don't really have that in architecting. So some of the theories for expected value, expected calculations, the average calculations, don't necessarily hold. And so we might have to use things like median and whatnot in order to do those calculations. That's ongoing work that we have as well. So future work, right? So kind of collapsing it down to those 3 different areas, those 3 different inputs to good decision making. So first, we need to understand the preferences by the architecting community, the architects, and the architecture to architecting stakeholders. So we need to do interviews and surveys and really get more an understanding of their preferences. We've got these high-level workshops that Army has done so far to provide us some guidelines, some areas to push, but we need more meat to that. We also need studies to determine the best techniques for transforming different preference measures to a common scale. Again, that's a huge issue. We're talking about doing net present value, but if these value units are all different along the time horizon, we can't do that, right? You need to be able to transform those into a common scale. And we need to understand the best techniques for aggregating multiple stakeholder preferences at specific time periods. We said maybe game theory is the way to go. That's about as far as we've gotten so far, because there's lots of different methods out there. And until we really get the common scale issues figured out and the preference issues figured out, that's one step too far right now. On the belief side, we need to understand risk preferences associated with the values that we care about here, which is slightly different than how we would understand risk preferences for money, since that's really just given to us as government employees. And we need to interview and survey architecture stakeholder communities to understand their risk preferences. So not only the architects' risk preferences, but the community's risk preferences. And that's because as we understand that demand model, their risk preferences come into play there, the community's risk preferences. We have to understand the sources of the uncertainty. So I've ignored that question the entire time so far, right? But these sources are key. So we have to understand the unknown warfighter environment. We have to understand changes in elected official desires, understand future technologies and their readiness. All of these things are going to be pulling into and impacting the uncertainties as we capture that probability distribution, right? I drew it really quickly. That's like decades worth of work to really figure that out, right? So a lot of hand waving, I know. We have alternatives that we have to do research on, right? So we have to formulate a methodology for generating new decision alternatives. Thankfully, there's a lot of work there that's been done by Stanford and other organizations about brainstorming techniques and idea generation. So a lot of that is done, in my opinion, except for the training part, which is a whole other issue. So the validity of the information sources need to be looked at, right? So not all information sources should be looked at as equals. You know, in design engineering, we have certain tests that are better, higher fidelity than others. While we don't have those tests, we can imagine that there's different information coming to the architect that needs to be considered differently. And we need sufficient documentation to show the justification to those future stakeholders and current stakeholders. So it's great that we can do it mathematically, but if we're not communicating it properly, it's all for naught. Now I'll leave you with one persistent question that we've had throughout the work that Army keeps asking us. And it's that, is architecting so uncertain that dominant decision strategies emerge, which enable more heuristic or axiomatic based decision processes? There's really a drive from the community to just have a few heuristics and say, this is always the best mechanism, the alternative that we should be selecting, right? There's really a huge drive for that. And mathematically, the first bullet point here would say no. There's no dominant decision, right? Because you don't know the preferences of the individuals, and you might have someone who loves costs for some reason. And all of a sudden, all your heuristics based on reducing costs change, right? The dominant decisions change. However, it's an open question. Because we don't know enough about the preferences, we don't know how aligned they might be. And so there might be something that's always good, right? There might be always the option to pick that free house, right? Instead of buying a house, but we don't know yet. So this is an open research question, but mathematically, the answer would be no. And so this is where the tradition of heuristics and the theory of mathematics is really colliding in the Army work. So with that, I know it was high level, but that's our proposed decision framework for architecting that we believe as long as we start doing research on these different areas will be a path forward, right? And we need to start somewhere. We need to have some kind of framework besides heuristics. And so with that, I'm happy to take any questions anyone has. Yeah.
Question and comment, maybe since I've been involved in this project.
Yeah.
So the business of architecting is based on precedence and always has been for the past 2,000 years. And the creation of an unprecedented architecture, as defined by Meyer, is also based on historical architectures. In this project, the Army has not allowed us to consider precedents in the design of architectures. They don't want to be informed by current systems. And so you might talk about how we dealt with that or didn't deal with that.
Yeah, so we've done a lot of work on, well, I'll talk about the challenges to that. And then I'll see where you're leading. I don't quite know where you're trying to lead me, but for the biases research that we have been doing related to this, working with the psychology department, there's significant concerns about looking at previous architectures because of the survivorship bias. So we have architectures that come through and they may look good and they might produce good systems. That's great, or may produce bad systems. However, there might be 20 or 30 architectures that never made it that far to producing systems. And so that one good system that you have from that one architecture with that one mechanism that we're looking at might have 30 different other architectures that if it would have went through the whole process, those systems might be garbage, right? And so we have this huge survivorship bias looking at past architectures that we have to be concerned about, and biases in general. So an architect may be working in a certain field like avionics or propulsion or some area, and they might believe that the heuristics and the information, the knowledge that they have in that field are applicable to other fields, especially when you bring things up to high level quality attributes and business drivers. And that's not the case, right? Very rarely, in my belief, because we don't have experimental data and we don't have the data to show this, but mathematically, it'd be very challenging to show that these couplings in this small subfield are related to these couplings in this other subfield in a way that we can consistently make good decisions. Phil?
Yeah. In your attributes of our architectures, have you looked at or been able to look at or allowed to look at technology roadmap?
No. We've been, so the attributes that we're examining are mostly utilities. And the relationships that we have been given are simply up-down arrows related to business drivers. The attributes that they're looking at have no time dimension to them. So road mapping wouldn't be possible in the current attributes that we have.
But these systems would have a lifetime of so many decades.
But they're not getting right. And we're not working with timelines right now in that we have an expectation that's going to be 40 or 50 or 60 years. We're showing mathematically we could do that, but there hasn't been data to given to us to use for that.
Yes.
There is a big emphasis by the Army to worry about time, right? Their argument is that the way that we're doing architecting right now is essentially we're ignoring the future states.
In which case you might be locking yourself in an architecture to something that might inhibit you.
Oh, 100%. Yeah, 100%. But if you're capturing the uncertain worlds, then at least you're considering those things.
Yeah.
I would also just mention quickly in response to that road mapping combines the architectural drivers and the key business drivers together. It has to. And the DoD is uncomfortable with business drivers. And architects.
Yeah. So while this is what you'll see in some, well, if I get back to it, this is what you'll see in a lot of DoD papers. This is ignored in a lot of the work that we've been doing, not by us, but by our Army sponsors.
I have a question that's maybe also related to the earlier comment of Tom, I don't know, but to what extent are organizational constraints part of the drivers and of your quality characteristics? Given the fact that we know that an architecture is always mapped in the end on how you organize things, and ideally organization follows architecture, but in practice organization is often a given, and it's no use to think of an architecture that doesn't fit your organizational constraints.
Yes. So in our framework, where that would fit would be in the preferences of the individuals. So if we're throwing an architecture in there that for stakeholder B or C or D doesn't work, like they don't even have a position in that to use it, or it doesn't make sense to them, then that would have significantly lower value for those individuals.
The preferences go beyond the heritage that you.
Yes. Yeah. So the Army is saying there's a lot of push on the quality attributes, but there's a ridiculous amount of preferences that we need to be capturing in order to fully represent the people.
And of course, and that's, I think we're linking with what Tom says, is your organization is also a reflection of your architectural choices in the past.
Yeah, sure. Yeah.
So there has to be a willingness if you really want to also consider radically different architectures, that you also change your organization. And
sure.
So it's not just a preference, it's at a certain moment it also feeds back into your decision making.
Right. There might be some education of stakeholders. So there might be this stakeholder A or B might really care about costs because that's all they've ever cared about in the previous architectures, right? And so there might be some training that, hey, cost isn't the only thing that we care about. There's schedule and there's other attributes or whatever it might be. So yeah, yes, if that was the point that you were trying to get to, Tom, yes.
The other comment we take is architectural patterns, research and stuff. And it's like, no,
there's a lot of emphasis right now from the Army through experimentations on attributes and trying to get the relationships. If we go back to this slide, trying to get the relationships between the quality characteristics and the quality attributes and the architecture and the quality characteristics, characteristics being the things that we can measure, the attributes being ilities. And they're looking there through the experimentation to see if there's dominant decisions. So going back to the last slide. The issue that I'm recognizing in some of that work, which is being addressed for future work, is that it's all so subsystem or system specific, because that's where we can actually analyze and measure things. And they're missing the architecture bit. So they're doing a lot of work, say, on networks and looking at the lags of packets depending on the network that you choose. But is that really an architecture decision that we care about at the very top level? That's more of like a subsystem decision in my view. And the worry there is that they're analyzing for patterns with that data that might not really hold for higher level architectures.
It was very clear when Charles presented this morning, you know, the evolution of the cloud to edge to device architecture. So this is a pattern that's evolving. They can't predict those future patterns.
Right.
So they don't want to deal with, right? And that's been part of the struggle.
Yeah.
That we've had.
But
But
that can translate in the fact that a very important quality attribute is flexibility.
That is a belief by the Army, yes. That is a belief by the Army for sure. The concern would be that can't be the only preference. That if you focus too much on flexibility, you start to lose a lot of other business drivers.
Of course, it's flexibility.
Sure,
Yeah.
sure, yeah. But yeah, the worry is that they're finding patterns to answer this last question that we had. But they're using data that might not be appropriate to make that solution.
And that they're trying to make systems that are more flexible, adaptable,
Right.
whatever in the future.
Right.
So they're trying to pull that out.
Thailand, yeah.
Thank you very much for the presentation. It was great and stimulating. So I have two questions. The first one is more of a concern. So as you were talking about the architecture and then you revisited this idea later on that some of the notions that you're talking about. So when I'm thinking about the architecture, I'm thinking about the functional and probable elements and their mapping to each other. And it has certain characteristics that I can focus on and I can measure, such as I can look at its complexity, modularity, etc. But then the design, embodiment design will be conducted afterwards once an architecture is set and the rest of the system will emerge. And then some of the other preferences that you brought up, such as is it performing well, is it affordable, etc. Some of those characteristics emerge later on based on the design, not specifically because of the architecture. Even though the architectural decisions dictate how those design decisions can be made, not all of the preferences are, I think, are belonging in the architecture space. There's another phase between this transition. And so how are you envisioning to break down these value functions to focus on these two phases of design?
Sure. So there's attributes that span different parts of the architecture that might have a focus on different parts of the architecture, where something like cost, there might be an architecture component. So as you're going through it, you're generating costs to generate the architecture, right? There's also the cost of the systems that are produced from the architecture. That should all be captured together. There's going to be high uncertainties as you go into the future, right? Especially with the system costs and whatnot. So I would say that there's attributes that have different focuses in different areas. And because it's an architecture, if you're caring about if that stakeholder cares about the systems specifically that are going to be produced and their performance, well, then those should be captured in their preferences. So if that person really cares about, if you're making an architecture for airplanes and you really care about the range of the systems that are produced, that has to be incorporated in. Is there going to be a ridiculous amount of uncertainty associated with that? Yes. Right. But it's doable. Is it where that uncertainty is so much that you can just ignore it because it's a uniform distribution? Maybe. We haven't gotten to there yet. So that's an open research question.
So my second question is how, so some of these system characteristics and the value generators, such as flexibility or interoperability, etc., only emerge in certain operational contexts. So at the end of the state of development, they might constitute a lot of value for the designers or the stakeholders, but there might be a case in the operational life of the system where this behavioral archetype never really comes into fruition. So let's say you only operate your system in nominal cases, then you never really need to change it. However, you might have had a preference for designing for flexibility early on. So I think in that regard, there's a lot of value in distinguishing between these different stakeholders and how to obtain value from the system. But is there a way to perhaps reconcile some of those considerations that might have been never really materialized later on?
So when you're looking at, so it's normative decision theory, right, would say that you're considering those future states and it's okay that they never occur. Right, but that at that point in time, that stakeholder would care about the flexibility, or they might care that this system could work in the Arctic, right? And we never end up in the Arctic. That's okay, as long as I'm designing or they're making decisions for that decision maker, that stakeholder that cares about that flexibility. That's okay. So it's a justifiable decision because that person cared about that. Now, do I need to appropriately capture the likelihood of that outcome and whatnot? Of course, right? But that doesn't mean that I would ignore that outcome, because that would bias everything towards a very specific mission or specific scenario. Does that make sense?
Yeah.
Okay. Yeah.
So I apologize, I ran to get a tea read in this the very first part. So you may have said this and I missed it, but I spent the whole rest of it trying to figure it out. What level of architecture are you really kind of considering here?
Yeah. So technically, this could be used at all levels, the
Technically.
framework, technically.
Right.
What we care about would be the enterprise level. So the Army has identified an enterprise reference and system, enterprise objective reference, something like that.
Yeah.
But there's 3 levels.
Reference, objective, which is family.
Yeah.
System.
Right.
And so I guess then kind of related to his point, the higher up you start, right? The much further removed you are.
Mhm.
It's almost like the next derivative down has to be reassessed. Because by the time you get to the unique implementations, right, the more you try to prescribe in terms of, you start talking about the purpose of architecture,
Mhm.
right? And so fit for purpose, and the more you try to prescribe and push that higher, the less flexible, right, it becomes going down. And so
Yes,
then you get
yes.
somebody who's like, well, crap, I can't use this because it doesn't work for me.
Mhm.
And so that changes a lot of the questions. I can offer that we have a group that has done some deconfliction abilities with respect to architecture analysis for the Army. But it is for a different purpose than an architecture leading
Sure.
to system design. It's an architecture leading to open systems, right? So completely different purpose. And so the mapping to quality attributes is a little bit different. But that gets back to, that trade of what is architecture for? Because if you're trying to be all modular and open, sometimes your performance cracks out, right?
Yeah.
Those are not one-to-one.
Yeah. And so there's a research branch that I didn't talk about here, but it's on deferred decision making. And it's when do you make that decision? Because you might push it to the next level to make it open, to keep it open, but you don't want to keep it open just to keep it open, right? If you want to,
But
you can make that decision.
we understand
Yeah.
what you were
Yep.
referring to. Thank you.
And we're over time, so we probably
Yes,
should go to
we
lunch.
are.
Yeah.
Thank you so much again.
Thanks.
Brian.